Good afternoon. Welcome back to the states of matter and gases and liquids. Actually, it is mainly the gases, liquids only, but there is a small interaction regarding the states of matter. That is nothing but the intermolecular forces. Intermolecular forces. Why it is required is a lot of importance is there in the gaseous states and all. Actually, the forces, whatever the forces acting on the one on other, because of that reason only we have all the three states: liquid, gases, and solids. So in these there are two kinds. One is attraction, another is the repulsion. Attraction, another is the repulsion. Attraction. Second one is repulsion. Repulsion. In the attraction, main is the van der Waal forces. Very, very small forces. Van der Waal forces. In this again there are three categories: A, B, C, and A is nothing but dispersion or London. Dispersion forces or London forces. What is this London? London is a scientist who found the dispersion forces. Is a London forces. It's a very big forces actually. That means when the two atoms are there and both are non-polar, but when they come closer together, electron density is only that mid, but when they come closer to each other, then there is an dipole moment will be there, induced momentarily, very big forces. So because of that there is an attraction. That is called the first type of this thing, dispersion forces are London. Second type is a dipole. Second one is a dipole. Dipole is very common. There is molecules like HF, HCl, like that. Wherever the other than water, don't take it as a water. Water is the separate category. That is the hydrogen bonding in the water walls itself that is separately dealt, because that is very strong dipole. So this is a charge separation is there, and because of charge separation there is a dipole moment. Because of dipole moment there will be attraction and so much. What is dipole moment? First we will say dipole is nothing but symbol is mu equal to charge density into distance. Distance will be in centimeters, charge density will be in ESU, and 10 to the power of minus 18 ESU centimeter equal to 1 dBi. That is the unit for the normally the dipole moment. Wherever the strong dipole is there, the attractions are more. The third category is called dipole-induced dipole. Dipole and induced dipole. Name itself is very easy. Induced dipole meaning is one is having permanent dipole like the HF, HCl and all this. Another one is because of this another atom is the non-polar atom is got the induced dipole moment. So there the attractions are called dipole-induced dipole atoms. So these are the three varieties of the mainly attraction forces, and another one is hydrogen bonding. These are the intermolecular forces. Because of this solids, liquids and gases formation will be there. Main example, if you see the H2O and H2S, one is a gas, another is a liquid. Both are hydrogen and both are the same hydrogen sulfur, both are the same families. But we will deal the subject in detail afterwards. So now coming to the negative effects. Negative is because of the gases particularly, they are in the random motion. Because of that thermal energy will be there. Means because of the temperature, the kinetic energy will be in the form of the repulsion. At particular moment there will be a balance between the repulsions and the attractions. So that is the main theories behind the gases before dealing with this. Why we have to deal with the gases first? Gases, though they are only the 11 gases are there. Entire table only 11 elements are there. 11 elements. One is 0 group 6. That is not much we are dealing. The second one is only 5. That is hydrogen, oxygen, nitrogen, fluorine, chlorine. 3 plus 2, 5. Only 5 are there. These are the only gases. But because there is a big chapters and big importance on the gaseous state, because we are living in the earth in the troposphere. We have mainly nitrogen and oxygen, a small amount of carbon dioxide and very other small amounts. So these two are the main elements as a gaseous. 78% is nitrogen and 21% oxygen, 1% is other gases like carbon dioxide and the two troposphere, which is very mean on the at the gravity itself. So we have to deal these things. And O2 and nitrogen are all this thing, hydrogen also. So before actually dealing the laws, we have some small nomenclature, means we have the not ideal gas, actually ideal gas we will deal separately. Gases are compressible. Gases are compressible. No shape. No shape. No fixed volume. No fixed volume. Lower density. Lower density. And mixes easily without any aid. Mixes easily with other gas without aid. Without aid. They exert the pressure in all the directions equally. They not one side it is more, one side they exert the pressure on in the container equally all the sides. So because of the with these postulates, now we will go by one laws where more prominent and the most important laws. First law, what is the first law? Is Boyle's law. He is also a scientist. Boyle, Boyle's law. What is it, Boyle's law? Boyle's law is nothing but P is inversely proportional to volume at constant temperature and mass. Mass I am going to represent with N, number of molecules or number of moles. This is the Boyle's law. Anyway, this also can be V is inversely proportional to, some people will say 1 by P also, but normally this is the representation. That means P equal to some proportion I am removing K1 by V at the same constant temperature and pressure. So K depends on the amount of gas and the temperature of the gas. So this can be rewritten as a PV equal to some K1 or K dash, whatever it is, V. Sorry, K1 K. PV equal to K at constant temperature and pressure. Now, so that means for a particular gas at particular temperature and pressure, volume if is P1 V1 equal to K1, and another temperature at a fixed mass, if it is P2 V2, then K2. So if it is K2 constant, but gas volume, gas amount is constant, then P1 V1 equal to P2 V2 at constant N. And T. So P1 by P2 equal to P2 V2. For a particular case, for a particular gas, these two are same. So P1 by P2 equal to P2 by P1 by P2 equal to V2 by V1. P1 by P2 equal to V2 by V1, P2 V2, P1 V1. Right. So this is the another way of expressing the Boyle's law. Now from this we can make some graphs. What is the graph? In the y-axis P, and if I am taking V as in the x-axis, there will be an isotherm. Isotherm is slowly coming down the pressure, and the when pressure is coming down, volume is increasing at particular temperature. So take T equal to some 200 degrees centigrade. Another temperature increasing, there will be one more isotherm, that will be some 300. Like this, as the temperature going up, the starting of the volume is equal to will be different, but volume is so this will be slightly, this can be represented in another way also. One more graph. P 1 by V, if you am taking 1 by V in the x-axis P, there will be this isotherm why I am talking is the temperature constant for a particular line, and there will be lines passing through the curve, means the center point at different temperatures. The slope will be more for the higher the temperature. Slope is more for the higher temperatures. This is the means at the constant temperature, and with one word PV equal to constant at T constant and constant, different isotherms. Isotherms means temperature is constant. This same one more in this itself we can say D also. D means density. Density we know density equal to mass by volume. So that means mass, if I am taking as a this thing density, PV equal to what we have written as K1. P1, P I am taking as it is, V I am replacing with D M by V. 1 by V I am replacing with M by D. This is K1. So on rearranging, K1 Pm by K1 equal to D. So on further this thing, that means D is directly, this if I am taking as a constant, P is directly proportional to D. That means the more the pressure, the gas will be more denser. In words, the more the pressure of the gas, it will be the denser. If the P is less, it is the low density gas. Okay, tomorrow we will see the Charles laws and other these things. Thank you.